A remarkable and unexpected discovery by the James Webb Space Telescope, JWST, has stirred the global scientific community, igniting serious conversations about the possible existence of alien life. At an immense distance of approximately 7 billion kilometers from Earth, JWST recorded an intriguing phenomenon, what appear to be artificial light signals coming from the surface of Proxima Centauri b, the closest known exoplanet to our solar system. These mysterious light emissions, described by scientists as resembling the glow emitted by distant metropolitan areas, have generated a surge of worldwide fascination. Could this represent the long-sought evidence of intelligent extraterrestrial life? The lights exhibit a pattern that appears too structured and consistent to be natural, prompting many researchers to reconsider previously held beliefs about our place in the cosmos. For centuries, humanity has looked to the stars in search of signs that we are not alone. Every unusual flicker and every strange atmospheric pattern observed on far-off planets has been met with equal parts excitement and scrutiny. But no previous event has sparked the imagination quite like this one. The James Webb Space Telescope, among the most advanced observational tools ever constructed, has delivered data so compelling that even typically skeptical astrophysicists are now entertaining the notion that Proxima Centauri b might harbor an intelligent and technologically capable civilization. The theory that the lights may be from alien-built cities is no longer relegated to science fiction. It now demands serious scientific investigation. Astronomer David Kipping from Columbia University has noted peculiar thermal readings from Proxima b, a rocky exoplanet residing in the habitable zone of its host star, the red dwarf Proxima Centauri. Unlike other rocky planets that absorb stellar light and emit infrared radiation in predictable ways, Proxima b behaves oddly. Its heat signature deviates significantly from expectations based on its distance from its star and its surface characteristics. These anomalies have made the planet a prime candidate for close study, particularly with JWST's unique ability to detect faint infrared signals. JWST's capacity to observe the planet's night side, perpetually hidden from its star, has been particularly critical in identifying these faint, structured light emissions. The lights detected on the dark side of Proxima b bear a striking resemblance to Earth-based urban lighting as seen from space. Unlike naturally occurring light sources such as lava flows or auroras, these signals display geometric shapes and consistent spacing, hinting at an artificial origin. Adding to the intrigue is the likelihood that Proxima b is tidally locked, with one hemisphere always facing its star and the other remaining in perpetual darkness. This condition results in extreme temperature differences, which might be mitigated by advanced technology. Some scientists suggest that a potential civilization on the planet could be using solar energy harvested on the daylight side to power infrastructure and lighting on the night side, a hypothesis that aligns well with the observed light patterns. Beyond detecting surface light, JWST is now being used to perform an in-depth atmospheric analysis of Proxima b. This is achieved by studying starlight that passes through the planet's atmosphere during its transits, allowing researchers to determine its chemical composition. Of particular interest are biosignature gases like oxygen, methane, and water vapor, as their coexistence often points to biological activity. Although JWST cannot directly detect oxygen due to its wavelength limitations, it can detect ozone, a secondary indicator formed from oxygen molecules and often linked to photosynthetic life. Meanwhile, water vapor and methane are more readily identifiable, though scientists must differentiate between biological and non-biological origins. Methane, for example, can result from both living organisms and geological activity, such as volcanic eruptions. The science of remote atmospheric characterization is both delicate and complex, but it remains one of the most promising ways to assess the habitability of exoplanets. JWST's ability to focus on extraordinarily narrow bands of light, up to 1,000 times finer than starlight, makes it particularly adept at isolating weak planetary signals. This helps scientists distinguish between thermal emissions from a planet's surface and those of its host star. Of particular interest are the rhythmic pulses of light detected from Proxima b, signals that remain consistent in both wavelength and duration. Some experts speculate these could be signs of structured energy systems or even artificial beacons. Others caution that natural explanations must be fully explored before leaping to conclusions about intelligent design. JWST's orbital configuration, also grants it the ability to monitor Proxima b continuously across its full day-night cycle, which lasts about 11.2 Earth days. This extended observational window is invaluable for detecting recurring patterns and confirming findings. In the coming years, scientists plan to augment JWST's data with observations from next-generation ground-based telescopes like the Extremely Large Telescope, ELT, slated to begin operations in 2028. ELT will provide greater spectral resolution and offer even deeper insights into exoplanet atmospheres. Despite the excitement, the scientific community remains cautious. Exoplanetary atmospheres are highly complex, and what appears to be a clear signal might have multiple interpretations. Moreover, JWST's reach is limited to relatively nearby exoplanets due to its sensitivity and orbital constraints. Therefore, astronomers are eagerly anticipating future missions that will more effectively suppress starlight, allowing for clearer imaging of exoplanetary surfaces and atmospheres. Still, even if the unusual lights on Proxima Centauri b turn out to have a natural explanation, the discovery marks a significant leap in our understanding of planetary systems and the potential for life beyond Earth. If, however, these lights do represent signs of intelligent life, the implications would be profound. Such a revelation would confirm that we are not alone, and that intelligent civilizations may have arisen elsewhere in the galaxy, perhaps even before humanity existed. This would not only revolutionize our understanding of science, but also reshape philosophical, religious, and cultural paradigms around the globe. The search for alien life has long fascinated humanity, though it has remained mostly speculative. Due to the vastness of space and prior technological limitations, with JWST we now possess the capability to investigate these mysteries with unprecedented precision. While challenges such as differentiating between biological and geological signals persist, the tools at hand are more powerful than ever. Even with its constraints, JWST has already proven to be a game-changing instrument in our quest to find life elsewhere in the cosmos. As scientists continue to dissect the telescope's findings and refine their models, the world watches with anticipation. The age-old question, "Are we alone?" feels closer than ever to an answer. Somewhere just beyond our solar system, intelligent beings might be looking up at their own skies, wondering the same thing. Though the evidence from Proxima b remains inconclusive, its potential to rewrite history has triggered a wave of scientific passion and public wonder. The potential confirmation of intelligent life on Proxima b would not only alter our cosmic perspective, but also demand a reassessment of what it means to be human. To imagine that another species, possibly staring at the stars as we do, has constructed vast light-producing infrastructure challenges centuries-old beliefs in our uniqueness. In light of this, researchers are intensifying their study of Proxima b's light emissions and thermal profiles. One hypothesis posits that a civilization may have installed massive energy systems, like solar collectors or orbital reflectors, explaining the remarkable brightness on the planet's night side. Once confined to the realm of science fiction, these concepts are now gaining traction in real scientific discussions. Scientists are investigating whether the detected light shows changes in a way that suggests artificial regulation, such as fluctuations tied to the planet's rotation or seasons, indications of structured energy use. Intriguingly, researchers are exploring whether these emissions follow patterns consistent with a technological timetable, such as peak brightness during specific orbital phases. If confirmed, it would support the idea of intelligent systems operating with purpose and predictability. JWST's long-term observational strengths make it ideal for identifying such sustained patterns, unlike short-duration missions. It can track Proxima b for months, enhancing the chance of detecting non-random light variations. In parallel, theorists are constructing detailed simulations of the planet's conditions, incorporating its mass, orbit, stellar radiation, and tidal forces to model possible climates and hypothetical civilizations. Given the unique environment around a red dwarf star, any intelligent life would likely have evolved under very different conditions than on Earth, adapting biologically and technologically to extreme temperature variations and intense radiation. Finally, one pressing question is the age of any potential civilization. If the lights have been shining for centuries or millennia, we might be witnessing the remnants of a once thriving society, either still alive or long extinct. Regardless of the outcome, the implications for science and humanity are profound.